So my name is Zlatinski. I'm a GPU software engineer for NVIDIA. I'm the lead engineer for Vulkan video feature at NVIDIA. And I'm also from the beginning of the video TSG group working on the Vulkan video standards. So we'll talk about Vulkan video today. How many of you guys work on video? Okay, apologies if it's too simple for you guys, if I cover some topics. And how many of you guys work on compute and graphics? Hopefully I don't put you to sleep with video stuff, so let's start. All right, this is what we're going to cover today, the Vulkan video roadmap. What do we have today and where we're going with the standards. Some general Vulkan video encode concepts, which are not going to cover really the standards, because those are huge standards, we don't have time. And last year I've tried to cover a lot of stuff and I ran over time. So apologies for that. So it's going to be more about how to deal with video in Vulkan. And so Vulkan video encode quality and rate control are the topics that I'm going to touch on, how to optimize video encoding. And some video tools if you want to debug your applications or you want to tune it is a topic we'll talk about. So API design goals. First of all, it's a low-level API. We call it API, application API, but essentially a HAL, very low level. It's designed for to be very, very close to the hardware, reentrant. You control all the resources, everything from the API perspective. Most likely, the way you use it is not from the applications, but using it to frameworks. Like we have design libraries to help with that. You've got FMPEG, GStreamer, open sources behind those standards. So most likely you guys are going to use it this way if you're application developer. If you're advanced coding developer, most likely you'll be digging deeper into the libraries and optimizing radio libraries and things like that. So one thing, it's a cross-vendor, cross-device API. By the way, it's not a GPU standard. It is an ASIC standard, so embedded system also could use it. When we design it, we make sure that there is nothing GPU specific there. And most of the companies that are involved, also they have ASICs for encoding and decoding video. We're not using GPUs pretty much for most of the encoding and decoding features. So when you're in control of all the resources and the features of the low-level encoders, essentially you have all the flexibility to change things the way you want to. You don't have to, in comparison with some simple-to-use frameworks, you don't have to go to proprietary companies and ask for features and small changes and things like that. So you're fully in control of that, and hopefully libraries which we develop will help to bootstrap or help with the complexity of the APIs, and you could start with those libraries and tune them up the way you want it to be tuned up. This allows for use cases where you have embedded devices with very limited resources to be used with Vulkan video, as well as you could use it for like streaming at the server side and high scalable applications as well. And so here's pretty much the charter we currently have. Last year we released video decode officially, 264 and 65. Beginning of last year, end of last year, December, we released also the video encode APIs and the 264 and 65 standards. Also, this month at the beginning, officially we released Vulkan video decode 81 spec, and we also have implementations for those. What we're currently working on is, or focusing on, if you will, is Vulkan video encode 81. We hope to be done, if it's not like third quarter, but at the end of the year, with the spec as well as some of the implementations. And also working on the encoder advanced high quality features, like quantization maps and adaptive quantization as well. So you're going to see Vulkan video is just, when it comes to the encoding, is at the beginning of its journey, if you will. So you're going to see even like the sample apps and FMPEG not being perfectly optimized, but we hope by end of the year, things to get up to par with the rest of the frameworks and capabilities of the encoders out there. And so those are pretty much the IHVs who worked from the beginning of the video THG group, NVIDIA, AMD, Intel, as well as open source. We really appreciate all these guys' contributions and hard work to get all these standards actually sorted out and working. It's not very easy to develop a very low-level HAL, which is universal between GPUs. So from one side, we don't want to have abstraction where application doesn't have control over the devices, but on the other end, there's so many differences between the different devices that it's sometimes very hard to get to this median point where all hardware would actually work in a very similar unified way. So when you develop applications once, they're supposed to work on any devices, regardless if it's Windows, Linux, embedded, and so forth devices, desktop. We really appreciate also the open source support for this. David Arley from Red Hat, he's been a very active contributor working on open source drivers, working directly with low-level devices. So we really appreciate there's already AMD and Intel open source drivers, and they continue to contribute to those. Also, Dave and Lynn from FMPEG, they're also helping with a lot of the AV1 standards by doing Mesa drivers before we even release the official drivers for those. So they released at the beginning of last year AV1 decoder for Mesa, and they're also working on the VP9 this year. So there's something that we really appreciate from the working group. We talked about support. It's very difficult, again, to just start working on the API. So we have open source project, which is targeting video decode and encode APIs. So the way we try to structure the sample is a set of libraries that you could use with example applications. So you could customize them and use them the way they are, or customize them or completely change them and use it the way we'd like to. Currently, the decoders are very well supported to 6465. They're quite robust because they're quite mature since last year. When it comes to the encoder APIs, there's still in alpha quality version. There's still a lot of development that needs to be completed before those are really production quality libraries, but we're trying to get there as quick as we can. And then we also have AV1 decoder, which is pretty much a done application, except there are minor issues with some content doesn't work exactly the way it's supposed to. But again, we're trying to get there as soon as possible, most likely next month or so. We hopefully to have a production quality AV1 samples. And very popular frameworks like GStreamer and FMPEG, Igali and Collaborate, as well as Lynn, that we really appreciate that they work on those standards, on those frameworks to make sure that if you're really a big fan of all these open source multimedia framework, which are very powerful, then you could use them pretty much from day one in Vulkan Video. So. Any questions so far? Sure.
Thank you. You mentioned that NVIDIA has a Linux support available today.
Yes.
Is a similar support for Linux platforms available by AMD as well as Intel?
Almost. As far as I know, when it comes to decoding, they're already done. They have encoder drivers for beta today, but they don't have yet release drivers. But I know that they're actively working on pushing this to the market as well. But they're very serious and they're actively working on, again, releasing those to the market. There's sometimes a chicken egg situation where you need to have CTS developed and then you have sample app developed and then make sure that your drivers work as well. So those pretty much got a bit delayed, but we hope by next few months for both companies to have those drivers sorted out as well.
Okay, so they are still working on Linux support. But-
Linux and Windows.
Sure.
And again, Dave from Red Hat, he's also working on open source drivers, which are also very good quality.
Yeah.
When
Sure.
it comes to both RADV as well as Intel.
That sounds good. Thank you.
Right, so let's talk about a little bit deeper. Hopefully it's not too much stuff. It's not too deep. Those are pretty much, if you were to develop applications for Vulkan Video Encode, those are pretty much going to be the stages you're going to deal with, where the first one in gray on the left side is going to deal with preparing the input images for the input of the decoder. As you know, you're feeding input images to the encoders and you expect to get bitstream out. And then you may have things like image filtering and image analysis for more advanced use cases. And then the red part in the middle, this is really what the extensions are targeting. Those are things like, for example, encoding the VCL data, which stands for video calling layer. Video calling layer, for people who don't know, is just the very heavy part that does require a lot of compute power to work on, which contains the header, a very small header, as well as additional data, which contains the bits and the pieces of the images which are encoded. So again, this is a hardware acceleration API, so we only take care of the really heavy parts to deal with in this case. And then the last part is the video elementary and container assembly. So this is something that application would actually handle things like headers, which are part of the elementary stream, or things like you're dealing with, for example, MPEG-4, for example, envelope, that you need to send additional information about describing the streams or multiple streams, or you're streaming, for example, you're saving in specific format, or you need to stream this through the network, then based on the protocol using real-time or any other protocols, then you may need to encapsulate additional network things to it, which are, again, beyond this specific standard. It's the responsibility of the application to deal with all this stuff. And most likely, if you're really planning to stream video encode, you won't see those things in the sample. Again, the sample only deals with the hardware part of things, the encoding and basic assembly. If you need to add messages and do more networking processing, then you either use some of the frameworks like FMPEG or GStreamer, or you probably most likely already have some frameworks that you want to use, and then you just plug in the libraries and use the outputs the way you like to. So if we were to dig a little bit deeper into the input stage here, so the one on the top, which is the encoder optimal input images. So in order for you to fit input images to the encoder, they have to be compatible with the encoder input. What does it mean? They have to be in the specific layout. Most of you already know there's a optimal layout and there is a linear layouts that usually we deal with when it comes to images in Vulkan. So some of when you actually do queries against the hardware, you'll see some of the devices will support linear formats, some will only support optimal. Some of the devices are going to support RGB input directly, some they would need to convert the RGB, for example, input to YCBCR. So based on the capabilities, most likely you may not need to do any pre-processing of the input images. Example for this would be, let's say, you're going to do transcoding. So what we try to do is, if you're using Vulkan to decode frames, then when you feed the frames directly to the, you could directly feed the images to the encoder because they're compatible. Or there is a new extension which we just released, which is YCBCR rendering, where you resolve the images directly. This is, by the way, Google extension that you could render directly in YCBCR space. You could create the images in the way that could be directly consumed by the encoders, right? And Khronos also is working on another extension that also allows for you render in RGB space, but when you resolve you also go to YCBCR space by defining exactly how this conversion would need to happen. So in those cases, you don't need to do any additional steps for this input preprocessing. Now, let's say your input does not support linear inputs, but you need to fit images from, let's say, a file, or you need to support images from other frameworks which are not quite compatible with the Vulkan images. Then in those cases, you need to stage your images. The way it usually works is that you have like a linear input as a buffer or another image, and then you schedule a transfer operation where the image is going to be converted to the input of the encoder, which is, if this is actually done correctly, we'll talk about this a little bit later, then it doesn't really, you won't feel any overhead or any latency with that. And in the last case, one of the use cases, of course, will be if you have an input file. In those cases, you still need input linear buffers, Vulkan buffers or images. And in those cases, you would copy the content or map the content to the buffers or images. And then your staging is going to copy those linear images to the input images, which are supported by the encoder as input. One more thing, which is most likely going to be needed with the new extensions we develop for the high quality, sometimes for very advanced use cases for the encoders. You need some kind of compute shader or some other hardware that calculates the quality maps, if you will, that are pushed to the encoder as a guidance of how to most efficiently encode the stream. So this is the image analysis stage, which today you won't actually even see in the samples. Excuse me. And so this is the main part of the encoding process. For some of you who actually have seen those extensions, you've probably seen that there are two parts of the extensions, which are, we have the encoder and decoder part, which are very generic and just deal with the submission to the queues of the work. But then the codec specific extensions, they contain a part which is, we call it KHR, which is like the Khronos specifics on how to primarily deal with the resources and how to glue the logic with the rest of the video encode and decode APIs. But the more important part is you're going to see also the standard headers. And those standard headers for each of the codecs we support have standard headers, and those headers, you'll notice that they're pretty much one-to-one representation of what the spec actually calls for specific fields in both headers and picture parameters. So if you're a codec developer, you just go to and look at the spec and say, I know those parameters because I've worked with those parameters forever, right? So it should be as straightforward as this. Also, if you're a codec developer, you'll know how to set in the best way the input headers. This is per frame data, as well as the parameter, picture parameter data, which is PPS, SPS, and BPS for HEVC as well. Those are not sent really each frame. Those are sent regularly, usually when you have, for example, change resolution is one example when you want to send those parameters, or you want to send them, for example, every, let's say, 30 seconds or a minute, just to make sure that the decoders actually are refreshed, they know what the parameters are in case they've lost them, things like that. So, but again, those are pretty much codec-specific rules that most of the codec guys are familiar with. And then there is, excuse me, commands that deal with the session itself. So most of you, if you've seen the standards as well, there is a video encode or decode session, which you always create in order for you to work with that. And this session contains the state of the entire stream. Things, before you start using the session, for example, you need to reset the session. If you need to change or update the quality of the content you're currently working with, there's a command for this. And there's also rate control settings, which we'll talk about a little bit later, that you need to deal with. And managing resources, again, this is a very low-level API, so anything from allocating input images, staging images, DPB buffers, allocating DPB slots, everything which is specific to resources is in control of the application. This is what makes the API so powerful that if you wanted to, you could actually tune up your application the way you want it. So if you're, for example, embedded device with very limited resources, you could really define to use much smaller DPB size buffers, and you could do things like, for example, putting allocating memory only when you need it. If you're using, for example, high scalability servers, then you may want to allocate a lot of resources and do them in parallel with hardware load balancing as well. So it's up to the application to deal with all this. And so for content that uses more advanced layout of the group of pictures, you need to reorder the input frames. Usually this comes through the reordering queues. Both video encoder and decoder, they work in decode order, not in display order. So display order, input order, whatever actually frames actually come in, they need to be queued. And when you submitting the frames to the encoder, they have to be in the encode order. We'll talk about a little bit later about this as well. So that's why you need the reordering. There is a DPB management that needs to be processed after the reordering or before. It's up to the implementation to do it. The sample app is doing it after. And so the DPB managing this is per frame as well as the per sequence. You need to manage. And there are two things. This is like a colleague specific part of the managing as well as the generic one, which is dealing with the resources. You need images for this, you need slots and so forth. So those are the things that need to be taken care of as well. After all this, you could do command buffer recording. This could be done completely out of order. And usually we tend to do it multi-threading in order for us to really reduce the latency. So if you have 8 CPUs, for example, you could spend 8 or 16 threads to do the recording. So most of the time you do all the work and you put the CPUs to sleep. This way you save power as well. And of course, the final stage would be the frame stream assembly, which is application-specific assembly of the based on the codec, if it's elementary stream or it's going to be specific envelope, which you're going to use. This is application-specific logic. You need to follow a protocol, if you will. And so this is a bit of a different view of all these things we discussed. So you could see the input frame data comes in, and then this data gets pushed to a queue which could support like transfer or graphics or compute based on what you're going to do. If you just need to change the layout, let's say linear to optimal layout, you only need a transfer queue. If you need to do more things like, for example, a color conversion, fancy filtering of the images, or maybe you need to do some other work, for example, if you want to generate like metadata for high quality video encoding, in those cases, you may need compute kernels as well. And so the output of this stage is usually the best way to optimize, to synchronize with the encoder is if you use Vulkan semaphores. You could use both binary or timeline semaphores. And then this would allow you to just submit work for this first queue, and then for the queue which does the real encoding, the GPU is going to wait for the work to be completed from this first queue instead of, for example, if you were to use the fences, you stall the whole pipeline by the CPU, you wait for the pre-processing stage to be done and then submit the work. This would definitely kill the performance and the latency of the application. And of course, after the video encode operation is done, again, the difference between those two queues is the first one usually works in input order or display order, and the second one works in the encode order or decode order. After the encoder is done with the stream, you would definitely need to know what the size was, because we deal with also variable size in the encoder. And so the actually reports, I'm going to show you the way the reports work through the encode feedback query. It usually tells you what the size was, what the encoder produced as output, and also going to tell you if there are any offsets, if you're going to do more complex sequence. And there's more things which I'm going to talk a little bit better later. And the final stage, of course, is the frame assembly. Now, I have a question for you. Is it possible for us to combine this first queue work with the second? Anybody? So can we, for example, submit, let's say I just want to do like transfer from linear to optimal for the input. Can I just do it in the same encode operation queue and then do like, for example, conversion to optimal and then encoding, conversion to optimal and encoding? Do you think it's possible? Anybody? Yes, it is. When you do queries against the queues, when you discover your video queues, those queues are going to advertise not only encode or decode operations, they're probably going to advertise other operations. So they may advertise transfer operations, they may advertise compute and so forth. So based on the implementation, it is completely possible for us to collapse this entire processing to just, as I described, you could do transfer operation where you transfer from linear to, let's say, optimal, and then do encode and so forth and so forth. And you don't even have to use semaphores or fancy synchronization, because when you do submission against the same queue in Vulkan Video Encode and Decode APIs, the implementation is possible to synchronize operations. So if you do transfer, encode, all we have to do is pretty much like doing the standard in-queue operations. You don't have to do semaphores and things like that.
Just want to clarify that. So depending on the vendor. Sorry, hello. And it's also a pleasure to meet you. So depending on the vendor, the way they implement it, it's possible. So would it be vendor specific? Like I would assume right now NVIDIA, you probably did that, right? But
yes,
it might not be possible with Intel or AMD, depending on what they release.
We highly recommend everybody to implement transfer operations in their encode and decode queues, but we don't want to really demand it, because we don't know if tomorrow there is a vendor who has a very low level power device that doesn't support that. So we recommend, but we don't say you must. Also, the first open source drivers that Dave has done, I don't think they've supported transfer. So when you go and query the encode and decode operations for the queue, you're going to see encode only or decode only. So you don't have a choice, but you have to do this.
Okay, thank you.
Yeah, sure.
I'll probably reach out to you later. Just thank you.
Yeah. So the important thing is that, and you're going to see this in the sample application if you're going to look at the code, is that since the frames are coming in display order or input order, we tend to submit the work right away if it's a separate queue. We submit the work to process the frames, because you have to delay sometimes the encode frames. There's like a, for example, I and B frames. There's a P frame. You have to wait for all these frames to come in before you say, okay, now encoder, go and do this batch of work. So we have to wait. But instead for you to wait for the input transfer operations, you could also use for example, the staging queue to start doing the operation ahead of time, and then the encoder is only going to encode the stream at the end. So it's up to the application to decide how, and you're right, it depends also on the specific IHVs, the drivers and capabilities and so forth. Sure. So this is just a list for you guys to go back and look at. It's just before you start doing any encoding, what you have to do, just to set up creating the sessions, creating the devices, queues, and so forth. This is something which is very well described in the specification, as well as the previous talks in Vulkanized, which are also the generic talks about Vulkan, we use most of the general concepts. When it comes to how you use images, how you use buffers, how you use memory, everything is all Vulkan. So if you're already familiar with this, putting aside the codecs, which we try to separate very well. So the codec specific part is handled by the codec guys or domain, and then the Vulkan side could be completely handled by Vulkan guys. So just time check. Okay. All right, so this is the last year presentation. This talks more about the Vulkan video core. So if you don't know what a video session is and for example, what picture parameters are and why we use them, probably you want to watch this one. All right, so again, different IHVs, different hardware, different drivers may have different capabilities and different limitations, right? So limitations could be the minimum size you could encode is, for example, 128 by 128. You can't go below that, for example, right? Or you may have specific limitations on rate control. If you were to change the size of the video, because what we support also in Vulkan video encode and decode is that you could locate the images only once, bigger images. Let's say you're going to stream 4K content, but sometimes you may want to go back to 1080p and switch back and forth. If you want to reduce the latency, you would probably locate images which are the maximum size you want to handle. And then it's completely fine for you to keep doing 4K images from like the encoder to the entire content. So you switch between 4K and 1080p, but you only use a sub image. So this is if you want to do it. If you wanted to, you could just change the images, right? So it's up to you how do you want to deal with that. So things like what will be the step at which you could really increase the size or deal with the size is another thing that some of the limitations. And then so the way the properties actually come is that you have the video capabilities, which are very generic for the entire framework. And then you have encode capabilities and decode, which is branching off. And then you have code-specific capabilities, which you need to look at to determine what can the hardware do and what not. So those are very important things for the application to consider before it starts processing all these things. Now, again, we try to develop libraries in a way that could deal with different devices and different capabilities. So things could be more straightforward, but until we get to the perfect libraries, then maybe something you have to definitely be concerned about. Now, with all this complexity, when we started so first of all, there's a big difference between the decoders and encoders in the standards. So if I were to say I'm supporting, for example, decoder which supports level 5.1 of 264, then I very well know what does it mean, right? I know maximum size of the DPB, how many slots I could use, how much buffering I could do, all 9 yards. It's pretty much predefined. So when it comes to capabilities and the way you deal with the decoders, things are much more straightforward. Now, the encoders, this is totally different story. It's like, first of all, you have different tools on your disposal. Some encoders support more advanced things, some not. Some support B-frames, some not. Some support different, they have different quirks where if you, for example, use specific set of picture parameters and specific header parameters, then you can do specific things, right? So initially, we tried to capture, imagine between all the hardware vendors, trying to capture all this information, putting them together, and trying to get to like a common ground, if you will, to describe all this to the application. And then we thought, oh, it's really getting too complicated. Now, application has to deal with all this very complex logic when they need to deal with video, so it's becoming impractical. So instead of doing that, we only advertise like a basic set of features for the encoders, the tools they support, and as I said, if they support B-frames or not, the quality levels, but anything else which is very specific to implementation, then we deal with this like with overrides. And so there are two types of overrides we deal with. The one, which is when it comes to picture parameters, those are that we send time to time, from the beginning, time to time to refresh. When you pass in, let's say, PPS and SPS picture parameters to the implementation, the implementation could look and say, okay, so you're asking me for specific tuning mode, specific quality, and those set of parameters to do things which most likely I won't be able to do. So instead for me to just return error back to the application and make things for the developer miserable to try different things, then what we do instead is we override some of the parameters which are not compatible. And by the way, they could be also things like somebody didn't know exactly how to set specific parameter, so they say it wrong. We also correct things like that with the picture parameters. So we used to ask the application to generate picture parameter bitstream data themselves before. Now, because of this, we stopped doing this. We say, okay, before you start using picture parameters, we're going to encode it for you. And in the process, we're going to also override all the data which is either incorrect or the hardware cannot handle, right? And so we're going to give you at the end the picture parameter bitstream, which you could just take and prepend to the VCL data which we generated at the end. We pretty much got like a good elementary stream to deal with. In addition to that, we could, if we had to override parameters, we're going to set this has overrides bit. It's going to tell you that, oh, by the way, some of the parameters didn't make sense or we couldn't handle it. So we're still going to handle the stream close to what you wanted, but it is going to pretty much work. Okay. Any questions about this? Excuse me. And check. Right. So the second part, so this is the part where you are dealing with picture parameters. The second part is the headers themselves. So this is per frame data. You're passing in like hundreds of parameters, specifying how the specific frame you want to be really encoded or compressed. The implementation determines that either some of the parameters are incompatible or the hardware cannot handle as well as it should. So in those cases, this also overrides. And pretty much when you look at the encode feedback queries, then encode feedback queries is one of the queries that Vulkan supports. Excuse me. You're going to have a bit which gets set which says overrides, which means when you decode the specific frame, the data, you get from the query the bit and you see, okay, so there's override. So it's not stop 100% of what the application requested for the headers. In addition to that, what those feedback queries, again, report is the size of the output in the bit stream, the buffer which you provided, how much of this actually has been really used. And if you have a more complex content, when you have like a multiple frames, back to back or multiple slices or sections of the encoder, then you're going to also see the offsets being populated for this in order for you to know how to assemble the final bit stream. Excuse me. Any questions so far? By the way, we have also a maintenance one extension, which we just released. This allows for, if you're familiar with Vulkan, when you do queries in general in Vulkan, you do begin query and end query before all operations. And so if you have counters, they apply to a specific set of commands or command that you want to cover. In video, this doesn't really make a lot of sense because you have, for example, one report per frame or per slice. And so what we have done in order for us to make things simpler for developers is we introduce so-called inline queries. Inline queries is like instead of saying begin and end, you just add a query as an extension to the encode operation, and then it's going to be populated and worked through the way it's expected. Another thing about maintenance one you may be interested in would be There's a structure which is called video profiles, which essentially is a format which describes the bit depth of the video and all nine yards which you wanted to work with when it comes to the input or output. And so we used to require this to be chained to all the operations. Like you allocate the image, you need the profile for video. You allocate the buffer, you need the profile. We simplify things based on the feedback from open source community. Now, for the inputs and the outputs of the decoder, you don't have to, only for the DPB buffers. So this simplifies things. So let's talk about this part, which hopefully you're not sleeping by now with all this info. All right, so you develop your application. Now you're going to start optimizing your encoder. You want it to get whatever quality you want it to achieve. Sometimes you may want to have, for example, very high quality videos, and you don't care too much about processing time. Sometimes you may want to do like real-time streaming. So you have to consider a few things that is just the first slide for this. First, you query how many quality levels does implementation support, and based on this, quality 0, which is the default one, is usually like the lowest quality, which could be probably a good quality as well, by the way. And then the higher you go to the quality levels, the better the quality of the encoded stream will become, but also the encoders will actually need to spend more time on this. So if you sometimes, for example, if you want to do 120 frames per second real-time streaming, you may not be able to fit in the budget with, let's say, 8K videos, right? So you have to be to see what the performance is, and you may need to dial back the quality level. And so the way you deal with the quality level, this is the encoder quality level info, which only contains the quality level. Then, excuse me, it's used in two places. The one is when you're creating the picture parameters objects, which are used in video, then you have to chain it there. So picture parameters need to understand what the level is. And the second place is you're setting it for the session. So the session again represents the encoded video stream. So you set it at least once, or when it changes, you also need to send a command for this. Apologies. Okay, so the second part for tuning, we try to make things quite simple for the applications, because different implementations, they have different tuning parameters for different use cases. Very much codec specific, hardware specific, implementations of drivers and so forth. So in addition to the quality level, what we ask you to do is to provide in the video profiles we just discussed that describe the formats. We also chain this structure, which is called video encode usage info. And pretty much what this structure contains is information about, or hints, if you will, how do you want to use the encoded content? Are you planning to, for example, just do transcoding, maybe a recording that does require, for example, a much stronger compression, or maybe you're going to do conferencing where you're going to need to do like a very low latency encoding. In addition, you have tuning parameters where you could be more specific. You say, I want the highest quality possible, or I want to have like a ultra low latency, for example, because I'm going to do conferencing. So all these use cases you describe in the structure, or maybe in the last bullet, if specific encoder support lossless, you want to have perfect images in and out. So you don't want to have any data quantization, for example. You could also do that. So you specify all this information, and again, you chain the usage info through all the profile info, and then both the session as well as most of the APIs are aware that what you're trying to do. So the implementation is going to optimize the encoder streams in the way you would expect it to. Excuse me. Now, one thing maybe I have to mention here, which is probably most of the coding guys know, is that quantization parameters, those actually the ones that directly affect the balance between video quality and compression level in video encoding. By quantizing more aggressively, which means you're increasing the value of the QP, in this case, the encoder reduces the bit rate of the video, so it shrinks it down, which is critical for streaming over a limited bandwidth or storing videos with limited capacity. So you increase the QP value, and then you're getting much less output of the encoder compressed, but then the quality may not be as good as you would like to be. So there's always a balance between them. And also, there's another thing which a lot of people may not know, the rate control. So the rate control is used by video encoders. Most implementations have this for achieving like a target bit rate by dynamically adjusting the QP values for different segments of the video based on complexity, details, motion, and other factors, which is essential for balancing video quality and encoded bitstream size. It plays a crucial role in the stabilizing video stream transmission by allocating a bit budget for each group of pictures or frames. We'll talk about this, ensuring efficient bandwidth usage and preventing unwanted buffering during playback. And so we support in Vulkan Video multiple modes, but the important ones are the constant bitrate. So this is ideal for live streaming, where a consistent bitrate is necessary to avoid buffering, ensuring stable transmission. So if you say, I want the output for the bitstream to be such for this frame or this group of pictures, then the encoder has to obey this if it's possible. And the other one is the variable bitrate. This is used in situation where video quality has a priority over the bandwidth usage. So allowing bitrate to fluctuate based on the complexity of the content. Or those are probably the most important things. And then there is the implementation-specific rate control, which maybe is not as interesting here. Now, just time check, okay. So setting the rate control in general, it is done in two ways. Even you probably know that there's a begin end command when you're doing like a video encoding. This pretty much encapsulates all the encoding or recording commands you're going to do. So one place to specify the rate control is at the begin. And the second, we need to change the rate control settings. So initially you have to set the rate control settings, and we need to change it. You also have to send the explicit command, which is video coding control info command. Now, if you really wanted to control QPs yourself, this is, by the way, something that we don't recommend, but you may want to, and I'll explain what those cases are. Then this is one of the modes which we support, which is rate control disabled. It means K implementation, I know how in the best way to do to encode the QP values for each frame, for each segment. So please don't do any for me. I'm just going to do a pre-analysis stage. I have very powerful algorithm. I'm going to calculate the values. QP map, by the way, is one of those where you could have your own algorithm and you could specify the area of the image which you want to have specific QP values. And then I'm going to program for each segment or each slide, slice what the specific QP is going to be. It's called constant QP value. So this is when you have when you really want to control this yourself with the application, then this is the way to do it. You set the constant QP for each slice, for each frame. And if you want to rely on the rate control algorithm, by the way, encoder companies spend a lot of time optimizing the rate control. And we have like recipes, if you will, for the encoders of how to achieve the best things you want to achieve. Again, we have from highest, for example, quality down to like lowest latency recipes. And really the rate control is the one that takes care of all these things by what actually it does is for each frame and each slice. It analyzes the content while actually you're submitting the frames in the encoder. And then all these values which you would manually set in the previous slide, those are going to be adjusted by the control algorithm. Now, what the responsibility of the application is going to specify the different parameters. So you want to specify, for example, what's the expected bitrate, the minimum and the average. If you're going to have like IP and B frames, what is going to be the range of the QP values that you wanted to set. Even you could specify pretty much the frame size of the different frame types. We'll talk about this quickly because it looks like I'm getting closer to running out of time. And so this is where the GOP structure or group of picture actually comes in place. For people who are not codec guys, you should probably know that iframes are pretty much self-contained frames. Video content always starts with those frames because there's no dependency on other frames. They're very robust because each time you get an iframe, you pretty much know that you're going to get video out, but they have a lot of data which they encode because, again, there's no dependency on others. P frames, they're so-called predicted frames. They depend on the temporal features of the video that from frame to frame, you're going to get a lot of similarity. So it exploits this, and P frame is only going to encode things which have seen in the previous frames, only differences without really encoding a lot of information for each frames. And the B frames is actually really going a step further. They're even more compressed. They exploit also not only like future frames, but also backward frames. So not only backwards, but future, I'm sorry. So in this case, B frames in the middle, they depend on IMP in this picture. And so in Vulkan Video Encode APIs, we describe the GOP structure with those parameters: GOP frame count, IDR period, and consecutive B frame count. So all these parameters, and this, by the way, from the specification, so you could go and refer to it, tells you pretty much allows you to define the structure any way you want it to. And as an application, you could also control the type of the frame. So even if you say, I'm going to specify a pattern like this one, when you have like P frames, and then you have 3 B frames in the middle, you're in the control, so you could change a frame type, and you could say, for example, I'm going to do like 2 more P frames instead of B frames. Now, there is a caveat that I wanted to mention here. If you're going to use thread control, you better actually follow the GOP structure. So you have to be careful about it, because when you have thread control, then we assume a specific structure that you're going to use to achieve the maximum performance you would like to expect the encoder to do. So if you start changing, like replacing B frames with P frames and I frames and so forth, then the whole algorithm is going to go nuts. Go quickly through the next one. Oh, by the way, IDR frames are the ones that reset pretty much the sequence. So there is no any dependency on the previous frames. And so you may want to send IDR frames periodically, for example, every 64 and 28 frames, just to make sure that if there was an error in sending data and there are problems, you don't have any dependency. So pretty much everything starts from like error-prone works, and also for searching content very quickly. Also, IDR helps a lot. And so I'm going to quickly go through this because I have only 5 minutes and I supposed to have time for questions. So those are pretty much the GOP patterns that we define as standard. The first one is just a simple, you have I and P frames. In the middle, you have multiple B frames, and there is only dependency on the I and P frames. The second one, which you could see here, is you have a more hierarchical structure of the B frames, where B frames are also references. And so the next B frame on the side depends also not only on the I and P frames, but also on the other B frames, bidirectional frames. More advanced and more complex structure, which not all encoders, by the way, support. So you have to make sure that in order for you to support the structure, then B frames and references are supported. And even more complex structure, I was planning to talk about it, but I'm running out of time. Apologies. So the final picture, sorry for the mess. So this sounds scary, but if you just wanted to build the structure in mind of how this whole thing works, is that on the right side, you're going to see, you set the quality level, you set the usage, and at the end, when it comes to the queries, you're going to get not only generic encoding parameters, which are recommended for you, but also going to get recommendation by specific vendor of what those parameters are going to be. So the rate control and everything looks very scary, but we try to make it very simple by saying, okay, now just tell us what you want to do with the quality levels and the usage, and we're going to tell you exactly the recipe of how we're going to generate the most efficient content for you if you follow those rules. So everything about the GOP structure and the rate control settings is recommended here. You don't have to exactly follow them, but you get the best results. And so this is pretty much, when it comes to the two codecs, what the related settings are that you may want to use for the algorithms. I'm not going to spend time on this. Quickly, development tools. Currently, NVIDIA offers NVIDIA Insight graphics and system profilers. You could see pretty much if you want to see any issues, specifically synchronization or tuning of the encoders, something doesn't work, then those tools definitely help. This, by the way, is the real capture engineer at NVIDIA was looking at why he was using like a hardware load balancing, and the two decoders actually did not really perform well. So when you look at the top level capture, you're going to see that because of improper synchronization duplication, they got serialized instead of being utilized in parallel. So those are tools that could help with some of the issues. So you could also see with the Insight graphics, you could see also, for example, graphics works, staging work, and you could see the decoders. And if you see things are not done, for example, fully utilized, if you will, then you're going to look for synchronization issues somewhere in the pipeline. Those tools, of course, work with general Vulkan graphics and compute. So, conclusions: robust cross-platform API for video acceleration with a lot of support from open source community and hardware vendors. We're expecting, by the way, this year or next year for embedded hardware vendors to have also implementation. So, some reference materials. You're more than welcome to attend GTC. There's going to be more talk about Vulkan video if you're interested. And graphics, of course, a lot of graphics heavy. And developer programs in NVIDIA that you could look for resources in general. I have, sorry, only 1 minute, sorry.
We got time for a couple questions. Thanks.
At least this time I fit into the time frame.
So in the case where you're taking raw video and I want to encode it in several different profiles or codecs, what would you recommend for best performance to get multiple encoding outputs?
So, so this is when you wanted to support multiple resolutions, is it?
Or like, let's say you want to go HVEC and H264 and AV1 at the same time.
Oh, okay.
Or two different profiles for H264 at the same time.
So it's again up to the use case you have. Are you targeting very high quality for transcoding, or you're doing like a broadcasting or real-time streaming and transcoding?
Let's go with that second case.
I'm sorry?
Let's go with that option.
Like streaming, for example,
Streaming.
sending it out.
So you're going to then set all your hints specifically for the case for very low latency, and most likely going to get recommendations not to use B frames. So it most likely is going to be only I and P frames to achieve the lowest latency possible, both from the encoder side and decoder side. And then you're going to be recommended not only the GOP structure, but also rate control settings and things like that.
And in that case, with all of those, would they all use the same video queue? Or would you have to create a video queue for each encoding?
Oh, it depends on the vendor again. We're planning, for example, we're planning to provide like a generic queue which has the encoders and decoders in the same queue as well as compute. going forward. It's not released yet as a feature, but you have to query the queue and say, all right, so I have one family here which supports decode only, another family which supports encode only, so you have to use two different queues. But realistically, we've done actually testing on the transcoding cases. You submit work for a decoder, and you take the semaphore from the work on the decoder, and you submit it to the encoder and say go, and you could pretty much go up to like until you run out of memory, and you let the GPU handle all this stuff. You don't have to either be in the middle of the CPU at all, except the assembly stage, of course, that you have to, take the individual elementary bitstream pieces and put them together. But you could, let's say, do like 64 frames submission, and you're going to see with the tool that they're all utilized frame by frame, and there's no really spaces between the utilization of the codecs. So doesn't matter if you're going to use separate queues and use semaphores, or you're going to use the same queue, it's going to be the same output event. So no concerns about that. If you're going to use the CPU with fences, then you definitely have to be concerned, because you're going to store the pipeline each time you need to work with decode or encode.
Thank you.
All right. Well, thanks a lot for coming.
Sorry, if there are no questions. Fine, yeah, I'll try. Thank you.